Okay, one thing we can do with the idea of kinetic energy, we can say that if the kinetic energy of a constant mass m changes by amount delta ke, starting with velocity v sub I, what is its new velocity? Okay, so can we answer that question? Now there are all kinds of ways we can answer it, but what we can say here is that okay, this means that one half mvf squared minus one half mvi squared is your change in kinetic energy. Okay. Now we assume that this is known, and this is known, and the mass is known. Okay. If we know those three things, well, we're left with only one thing that we don't know, which is VF. So we can easily solve for VF. And we see that one half mvf squared is going to be delta ke plus one half mvi squared. So we're going to have this on the right-hand side of the equation. Okay? And on the left-hand side, we're going to have one half mvf squared. So if we multiply by 2 over m, we get VF squared, but of course we want VF. Hardly left myself room to make the square root sign, but there it is. Okay? So we have this. Now that's not a formula you want to remember or memorize, although if you have a photographic memory, there are all kinds of ways you can rearrange these relationships, declutter your mind with a bunch of formulas. Okay? It's a process. So let's just suppose you have that, well, we haven't talked about the units. The point is, if you know your change of kinetic energy and your mass and your initial velocity, you can figure out your final velocity without having to go through the equations of motion or any other kind of analysis of the motion. Doesn't even, as it turns out, matter if the acceleration is uniform or not. Okay? Now, we've derived this just for the case of uniform acceleration, as F net and m were constant. So an important fact is we haven't proven it, but gets a little complicated. Get into differentials and quotient rules and all kinds of stuff. We don't want to get there yet. So I'm going to say this applies whether F net is constant or variable, because the whole change in kinetic energy equals work done by the net force. Is easily enough derived using calculus. Okay? Right now, we're just going to go with this derivation. I'm going to assert this, and then we'll do a calculus derivation later. It's very simple. Okay, so that's one important aspect of this. We can do this whether or not net force is constant or variable. And we can't use the equations of uniformly accelerated motion if the net force isn't constant. At least net force of a constant mass isn't constant, okay? Okay, well, I want to talk about the units of these quantities for a minute. Okay, work. As units of force times delta x. Now the work done by the net force is the net force times delta x, but work in general by any force, whether it's a net force or not, is the product of that force and delta x. So what are the units of F? Well, the units of F, remember that F equals ma. So units of F are units of mass times units of acceleration, kilogram meters per second squared. Units of delta x are meters, and then I'm talking SI units. Units of delta x are meters. So units of work are kilogram meters squared per second squared. Okay, so when you multiply kilogram meters per second squared by meters, which we have to do, of course, we get a meter squared. Okay? Now, kinetic energy is 1/2 mv squared. It's very obvious, we know what the units of mass are and the units of velocity. Leave the velocity is a meter per second. Squaring that, we get meter squared per second squared. And then that's multiplied by the kilogram. So the units of work and kinetic energy are the same. Now, another way of writing these units is clearly kilogram meter squared per second squared is kilogram meter per second squared times meter, which equals newtons times meter. Newtons being the unit of force. Okay, so units of force are this, and I could say that a kilogram meter squared per second squared is a newton, so that the unit of work or the unit of kinetic energy could be written as a newton times a meter. And newtons times meters is joules. That's just a name we give it. And Joule is a guy that did a lot of research on some early thermodynamics. I think was involved with boring out chunks of metal and make candles. You have to keep cooling it. You evaporate a lot of water when you do that. And you look at the energy changes. I think that was Joule. But Joule then, took that, if that was the origin of it in his case, and investigated it very carefully in the lab. Okay, and came up with some pretty profound stuff. I realize a lot of this. Okay, so those are some units. We've got units of newtons, unit of force. Okay. We've got units of work, which is joules. Okay, so let's go ahead and look at a specific case. And let's just say, take a very simple. First of all, if the kinetic energy of a mass m is that's a clumsy statement. Let me state it a little less clumsily.
Thank you.
Still kind of clumsy. Okay, so if a mass m has kinetic energy Ke, what's its velocity? Okay, well, if its kinetic energy is Ke, then 1/2 mv squared equals Ke, and we solve that for v very easily. V equals the square root of 2 Ke over m. And we don't need to remember this, although you're probably going to use it enough that you remember it. But remember this, and you know how to get from this to this. You know that this is how we relate mass and velocity to kinetic energy. Okay, so if a 2 kilogram mass has velocity 60 centimeters per second, and you can think back to the lab where we had a cart that might have been 2 kilograms, and you can think of that moving at 60 centimeters per second, not that fast. Then what's its kinetic energy? Now that one's really straightforward, because you got the definition of kinetic energy, 1/2 mass times velocity squared. Well, Ke is then 1/2 mv squared, which is 1/2 of 2 kilograms. Now we want to do this in SI units, and centimeters per second is not SI. That's 0.6 meters per second, quantity squared. And we multiply that out, that's 0.36. And we get 0.36 kilogram meters squared per second squared, which is the same as 0.36 newtons times meters, which is the same as, of course, 0.36 joules, depending on what we're trying to do with the information. We could express it in any of these three ways. Okay? Now, let's say that whatever force gave this 2 kilogram mass that 60 centimeter per second velocity is applied, and there's some I'm leaving out there, but is applied to something of mass 10 kilograms. Okay? So then the 10 kilogram mass would have the same kinetic energy. So and I'm going to change 10 kilograms to 8 kilogram mass. Okay? Well, we then know that, again, 1/2 mv squared equals kinetic energy. So in this case, kinetic energy is 0.36 joules. That's 1/2 of 8 kilograms times v squared. Well, half of 8 kilograms is 4 kilograms. We divide that into the 0.36 joules. And I'll actually write that out, 0.36 joules over 4 kilograms equals 0.09 joules over kilograms. Okay? Now what's a joule over a kilogram? Well, a joule is, I'm going to do this in a little more detail than you probably want to, but we're going to see if we can articulate this unit with kilograms. Of course we know we can't because of what we've just seen, but it's typically how we want to think in terms of units, okay? Well, this doesn't help a lot. The joule is a newton times a meter. It doesn't help us to divide a kilogram into the numerator. Now naturally what we need to get here is we need to get meters squared over seconds squared so that when we take the square root we get meters per second, right? And we don't just assume that our units are right and that we're going to get that. We write out the units and we analyze them. And we're going to say, okay, well a newton of course is a kilogram meter per second squared. Times a meter divided by a kilogram, and now the kilogram divides the kilogram, the meter multiplies the meter, we get 0.09 meters squared per second squared. Okay? So now V is going to be plus or minus the square root of 0.09 meters squared per second squared, which equals plus or minus 0.3 meters per second. And we have to have the plus or minus there because we don't know in what direction things moving. Okay? This information doesn't tell us in what direction either of these objects is moving. Okay, well note this is half the velocity of the 2 kilogram mass with the same kinetic energy. Okay? But of course, this is 4 times the mass. Does that make sense? Well, four times the mass has the same kinetic energy, but half the velocity. We have a mistake here. Shouldn't it be 4 times the velocity, or 1/4 the velocity? More kinetic energy, more mass with the same kinetic energy is going to have less velocity. Well, no, that's not a mistake. Kinetic energy is 1/2 mv squared. Emphasis on the square. So it's proportional to mass and squared velocity. Okay? So, means if you have twice the mass, you have 4 times the mass, and half the velocity, then you have a fourth of the squared velocity. Okay? So half the velocity and 4 times the mass gives us 4 times 1/4 of the kinetic energy. And 4 times 1/4 of the kinetic energy is the same kinetic energy. Now, one way or another, you should understand this very, very thoroughly, because understanding the proportionalities involved in the various relationships we use in physics and everywhere else is really essential to understanding those relationships. So you want to start by understanding this. Now, we can do proportionality formally, but I'm stating it kind of in the vernacular because you really want to understand it in the vernacular. You want to understand it formally as well, and I strongly recommend that you study what has been neglected in the curriculum. But there it is.